I was asked a couple of months ago to say something to the ATI doctoral training students. In fact, I was asked to cover the whole of statistical methodology and theory in 3 hours, which did leave me slightly wondering what I'd do with the other 2 hours. So there are many different approaches one could take. The initial one I took was no way. But then I thought about it a little bit more, and I thought, well, there is a sort of story I can tell. Of course, it's completely impossible to cover the whole of statistical theory and methodology in 3 hours. But rather than just sort of skating over everything completely in a very wishy-washy way, what I thought I'd do is sort of follow one particular theme that I think has been very prominent in statistics over the last 15, 20 years particularly, and how we get there. And so this will sort of take us on a journey from some very classical statistical models, in particular the linear model, which is at the core of statistics in many ways. And then we'll move on from there to high-dimensional statistics, so getting much more towards sort of modern data science, and we'll talk about the lasso as a way of doing automatic or simultaneous variable selection and parameter estimation. So yeah, we're going somehow from the 1930s through to the 2000s, and I hope it'll be an interesting journey, but let's see. So I think first we should begin by congratulating the ATI staff for the wonderful job they have done at improvising these boards at very short notice. I don't know how visible that is to the people, if anyone's watching online, but it's quite a remarkable feat of engineering, let's just say that. But I am going to be writing on the board, so if you think you can't see the board from where you're sitting, you might want to think about moving. Okay, so the first sort of hour or so is going to be very classical stuff that I would cover in a first undergraduate course in statistics, but it'll sort of hopefully get us all on the same page from where we can move on to more modern things. Okay, so yeah, I'm going to be talking initially about linear models. Can everyone read that? Yeah, okay. And let's start with some classical theory. So the backdrop here is that very often in statistics we're interested in understanding the relationships between different variables. In fact, often between a response variable that we're particularly interested in and the way it varies with one or often more than one predictor variables, also called covariates or explanatory variables or independent variables. So these things have lots of synonyms. Okay, so we're going to be interested in particular here in the situation where we have y1 up to yn be independent responses with yi being distributed normally about mu I and with variance sigma squared, where mu I can be written as a linear combination of xij beta j for some known covariates xi1 up to xip and unknown regression coefficients beta 1 up to beta p. Okay, so this is the linear model usually written as y equals x beta plus epsilon, where y is my vector of responses, x is what I call my design matrix, so it's an n by p matrix, beta is my vector of regression coefficients, and epsilon is my noise term, and it's got an n-variate normal distribution with mean vector 0 and covariance matrix sigma squared times the identity. Okay? So I hope most of you, if not all of you, have seen this model before. Okay? Okay. So I start writing about here. Is that okay? Yeah. So classically, we assume that P is less than n and that X has full rank P. So the columns of X are linearly independent. Okay? This means that X transpose X is positive definite because if I've got a non-zero vector Z in R to the P, then Z transpose XZ is just a squared norm of X times Z, and since Z is non-zero and X has got full rank, this is positive. Okay? Okay, so let me write beta hat and sigma hat squared for the maximum likelihood estimators of beta and sigma squared. So here's a quick warm-up exercise. Show that. What's the formula for beta hat? No. So it's X transpose X inverse X transpose Y. People seen this formula or not? Yeah? Okay, good. And the distribution of beta is normal, beta hat, sorry, is normal about beta, and with covariance matrix sigma squared times X transpose X inverse. Okay? So this is an unbiased estimator of beta, and it turns out that this is the smallest possible covariance matrix that you could get among all linear unbiased estimators of beta. That's what the Gauss-Markov theorem tells us. So the second part of this exercise is to show that sigma hat squared is 1 over n times the square of the length of the residual vector, and what's the distribution of sigma hat squared? So it's got a sigma squared over n times a chi squared n minus p distribution. Okay? So in a classical situation where p is small by comparison with n, we know that the expected value of a chi squared n minus p random variable is n minus p. So If p is small, then this is approximately unbiased, but not exactly unbiased. Okay? And the variance will go to 0 as n increases. And then the third very important property about beta hat and sigma squared is that beta hat and sigma hat squared are independent. Okay, I think I'm glad I'm starting from the beginning here. Good, okay, so these are really absolutely crucial properties of our maximum likelihood estimators. Notice that the vector y hat, which is x beta hat of fitted values, satisfies that y hat is x into x transpose x inverse x transpose y, and that I can write that as p times y, where P is this matrix here, is a matrix representing the suspense will kill you. Representing an orthogonal projection. In other words, p squared is p and p transpose is p. Okay? So notice that I don't say it's an orthogonal matrix. It's definitely not an orthogonal matrix. It's representing an orthogonal projection, and it maps y onto the p-dimensional subspace U, which is the set of xb for b in R to the p of Rn. So has rank p. Okay, the dimension of its image is p. Okay? So in other words, we've got the following picture. Here's my origin, here's my vector y, and this is the subspace U, xb for b in R to the p. And what I'm doing when I'm fitting my linear model is I'm finding the closest approximation to y within this p-dimensional subspace. Okay, this is py or x beta hat. So I'm trying to explain the variability in my data. I've got n variables, n responses. And I'm trying to explain this variability in terms of a smaller number of variables, p variables. Okay? And the way I do this is sort of to realize that the best explanatory, the best fitted value I can hope for within this subspace is what I get by projecting the response onto this subspace. Okay? Any questions about that? So now, suppose we partition x and beta as x is x0, x1, where this is n by p0 and this is n by p minus p0, and my beta I'm going to partition as beta 0, beta 1, where this is P0 components and this has P minus P0 components. Okay? And that we're interested in testing a null hypothesis that beta 1 is 0 against the alternative that it's not. Okay? So this is one of the most common things that practitioners want to do with their data. They want to know, do I need this variable in my model or not? Okay? So what we're going to study is how would we try to assess whether or not we need a subset of all the variables within our model. Okay? Is age a relevant explanatory variable, a relevant covariate in my model? Is a sort of very common sort of question you might be interested in asking. Okay. Well, under H0, we've just got a smaller linear model, so the MLEs are beta 0 double hat, which is x0 transpose x0 inverse x0 transpose y, and sigma hat squared, or double hat squared now, y minus x0 beta 0 double hat squared. Okay? So we've just got a smaller linear model. And the fitted values y double hat satisfy x0, x0 transpose x0 inverse, x0 transpose y, and that's what I'm going to call P0y, where P0 represents an orthogonal projection onto the P0 dimensional. So don't be confused, there's a capital P0 for the matrix and a little P0 for the dimension. Subspace, which I'll call U0, which is this guy here. So in other words, we can now think about augmenting our earlier diagram, representing what happens when we fit linear models. So here's my origin again, and here's my response vector y. I know that fitting my larger model amounts to projecting it like this, but fitting my smaller model amounts to an orthogonal projection onto this guy here. Okay? And the question is, which of these do I prefer? So, which model do I prefer? So, what would give me evidence that the smaller model wasn't true? Well, this is a smaller dimensional subspace. I'm representing it with a one-dimensional subspace. This one I'm representing with a two-dimensional subspace. One thing I know is that projecting it onto the one-dimensional subspace has got to leave me with a longer residual vector than if I project it onto the two-dimensional subspace, right? So whether I should prefer the smaller model or not should be related to the relative lengths of this residual vector to this one, right? So what I'm going to do is let L0 so this is going to be the log likelihood under the null hypothesis. And then I've also got a log likelihood under the alternative hypothesis, which is very similar. So these are my two log likelihoods, okay? And it can be shown, it's actually rather straightforward to show, that the likelihood ratio statistic, so the way we usually test hypotheses is by looking at the likelihood ratio. So I can write this as W and then LR for likelihood ratio for testing H0. So this is defined to be twice the log likelihood under the alternative evaluated at the maximum likelihood, estimators, minus the same thing for the under the null hypothesis, is a strictly increasing function of what I'll call f, which is defined to be this scalar factor 1 over p minus p0 times the ratio, well, it's like looking at the ratio of two residual vectors, or squared length of two residual vectors, but just normalized appropriately. So let's have a look. Py minus p0y, that's this distance, that's this vector here. So I'm looking at the square of the length of this guy and its ratio to this whole guy from here to here, right? So I'm saying that if this guy is long relative to this one, that gives me evidence against the null hypothesis being true. Does that make sense? Right? So it's convenient to write it in this way because then this vector and this vector are orthogonal, and therefore, because we're in a multivariate normal world, that means that they're independent. So the numerator and the denominator of this expression are independent. Who can tell me what the distribution of this ratio is? Under the null hypothesis. Sorry? No, not chi-squared. It's a ratio of two things that have got chi-squared distributions and then scaled appropriately. But it's not itself chi-squared. The clue is in the letter that I gave it. it's got an F distribution. Okay, so we therefore reject H0 if F is bigger than what I'll write as Fp minus P0 n minus P alpha, where this is the 1 minus alpha quantile of the F P minus P0 n minus P distribution. Okay? So, now I want to show an example, and I'm going to do it in the form of a demo in R. Okay, so the data I want to look at is it's a cars data set, which is one of the built-in data sets in R. And just to emphasize the fact that this is very classical theory, it's going to be, we're talking about the speed and the initial speed and stopping distances that take for cars recorded in the 1920s. Okay, so we're talking about initial speed in miles per hour and stopping distances, of course, in feet. Okay, so here is the cars data set. There are just 50 cars that we're talking about. And I'm just going to plot the data so you can see what they look like. Something like that. Oh, that's interesting. Okay, the display settings aren't quite right on this screen, I think, but I guess it'll do. Okay, anyway, so if you look at that data, your first instinct, I think, would be to try and fit a straight line through that data, right? So we're going to do that, but we're going to take into account one fact that I claim is relatively clear, which is that cars that start with 0 initial speed don't take very long to stop. Okay? In fact, they take 0 distance to stop. So I know that my regression line should go through the origin. Okay? So I'm going to let x0 denote the first column of the cars data set, and y, my response, the stopping distance, is going to be the second column. And then I'm going to fit a model of y against x0 without an intercept. So that's what the -1 is doing there. And if I look at a summary of this model, then I get something looking like this. And I can see the coefficient, my gradient for this line is 2.9. And it's easy to impose the these are the fitted values that I get from my curve from fitting this model. Okay. Now that doesn't look too bad, but if you know something about the physics of car braking, you might think, well, maybe I need a quadratic term in that model, right? So how could we do that? I could create a new design matrix X, which is what I get by putting together x and x0 squared, x0 and x0 squared. So I get a new, so 50 by 2 matrix now, x like this. Okay. Now I fit my model again without the intercept, but I also need to add in the well, I could do this in different ways, couldn't I? No, this is okay, just like that, x like that. So now, if I look at the summary of this guy, then I've got a coefficient, the sort of linear term, and then the quadratic term in my model. Okay, so it's not quite so easy to fit this on the to put the vector of fitted values on, but it's not too difficult. If I create a sequence going from, say, 0 to 30, length something like this, then I can add a line to my plot. So I need to extract the first coefficient of this model and multiply it by x, and I add the second coefficient and I multiply it by x squared, and I've got to do it in a dotted line, and then this is my vector of fitted values. Okay? So the question is, which of these models do I prefer? Okay? I've created this orthogonal projection here, I've created the orthogonal projection here. Which one do I prefer? Well, the easiest way to get R to show you which one you prefer is just to do an ANOVA test between them. Okay, and this tells me that my F statistic is 9.4 with a corresponding p-value of about 0.35%. Okay, so certainly I'd regard this as significant, and I should be including my quadratic term in my model. Okay, if I want to compute this by hand, then what should I do? I should create matrix P0, which is x0 times the inverse of x0 transpose times x0 times the transpose of x0. And I do the same with P. And I know that my n is 50, my P0 is what here? What's P0? How many parameters have I got in my null model? 1. And what's my P? 2. Okay, so now I've got to compute this ratio here. I don't trust myself with all the brackets, so I'll do it, the numerator and the denominator separately. So if I look at the sum of P minus P0 times y, and I square that, and then I divide that by P minus P0, and then I've got a denominator which is y minus P times y, and I square it and I divide that by n minus P, and then I compute the ratio of the numerator to the denominator. Then that's my F statistic there, okay, which exactly is agreeing with what we found from how R did it. And then if I want to compute the p-value, I need to look at the appropriate quantile of the F distribution evaluated at this capital F with p minus p0 degrees of freedom and n minus p degrees of freedom, and I get exactly the same p-value for the test. Okay, so that is something. This sort of analysis is something that gets done on, not a daily basis, not an hourly basis, a second by second around the world. People are doing this type of analysis, right? Any questions about it? No? Okay. So I want to finish off this little chunk of material on the sort of classical theory with a lemma that's going to talk about the performance of my estimator. So in particular the performance of beta hat. Now there are different ways you could think about the measuring the performance, but the two of the most obvious ones are in terms of their prediction properties and estimation properties. So this lemma is going to come in two parts. And the first part's going to talk about prediction. The second part's going to talk about estimation. So, if I look at the expected value of the average prediction error that I make on the observations, my claim is that this is equal to sigma squared times p over n. Okay. So you might call it, this does often get called prediction error, but in some ways it's more like a training error, because I'm computing the error in the fitted values at my observed x is. I'm not sort of observing a new x. Right? And then the second part says that if I write omega for 1 over n x transpose x inverse with entries omega ij, then the expected L1 distance between beta hat and beta is sigma over n to the half times a sum from j is 1 up to p of twice the diagonal entry omega jj divided by pi, and then take the square root. Okay? So this is talking about the estimation error, how well beta hat is actually estimating the unknown parameter beta. Okay. Well, the proofs are fairly straightforward, so let's give them. So I want to think about the distribution of x times beta hat minus beta. Well, we said that beta hat had a p-variate normal distribution about beta. So if I subtract off beta, then this guy's got a p-variate normal distribution about 0 with covariance matrix sigma squared times x transpose x inverse. And when I multiply it by this x here, that means that this has got an n-variate normal distribution about 0 with covariance matrix sigma squared times p. So if I want to think about the expected value of the average prediction error, well, I can take the 1 over n out of the expectation, and then I'm just looking at the sum of the marginal second moments of this random vector, which means that I get a sigma squared over n, and then I've just got to compute the trace of this matrix P. Okay? But the trace of the matrix P, remind ourselves what P is x transpose x inverse times x transpose. And then the trace is invariant to cyclic permutations of its arguments, so I can move the x over to this right-hand side here. But this is just the identity matrix in p dimensions, so this is sigma squared times p over n. Okay? And then for the second part, well, we can write that beta hat minus beta is p-variate normal about 0, and then by the way that I've defined this omega, I can write this as sigma squared over n times omega. So since the expected absolute value of a normal 0, 1 random variable is the square root of 2 over pi. I'm being sloppy when I do this, okay? I should really write the expected absolute value of a random variable, where that random variable's got a normal 0, 1 distribution, but I'm being lazy. Don't do this, okay? The expected L1 distance between these guys, so I've got to think about the standard deviation of each component, and this is giving me a sigma over the square root of n, and then I've got to think about the diagonal entry of this covariance matrix, multiply it by the expected value of what I've got left, the normal 0, 1 random variable, and I do get exactly what I claimed, 2 omega jj over pi. Good. Okay, so these properties are going to be useful to me when I come on later on this afternoon to talking about the lasso and the theoretical performance properties for the lasso. Okay, we'll see how these compare with what happens in a high-dimensional setting. Okay, so that's really all I want to say about very classical linear models. Okay, we're now going to be thinking about a situation increasingly common in today's big data era, where you're collecting more and more variables that might explain the variability in the phenomena that you're trying to observe. So let's go back to the cars data. We only measured the initial speed for a variety of different cars, but you can easily imagine other factors that might well influence the stopping distance. The road condition, the weather conditions, the depth of the tyre tread, okay? There are all sorts of other factors that probably, you know, it was too difficult to record back in the 1920s, but nowadays it's so easy to collect and store data on those previously unimaginable scales that we very quickly end up with huge numbers of variables that might be relevant to explain the variability in the response that we're observing, and at least initially we're not sure which ones we really need in our model and which ones we don't. Okay? So I want to argue though that the rules of the game somehow change a bit when the dimension gets large. And what was a good estimator in the low dimensional settings is no longer good when the dimension is high. So just look at this ratio, we've got P over N here. Well, very often in all sorts of modern data, we might have P much bigger than N. Okay, if you're working on microarray data, you might have many thousands of genes that might be relevant for explaining the variability that you're seeing in your response of interest. And only tens or, you know, even in the ideal case, hundreds of repetitions of the experiment. So this guy is not going to be small. Okay? And I want to argue that a sensible way to proceed in those sorts of situations is to shrink the maximum likelihood estimator towards the origin somehow. Okay? And the first step in this direction was to think about ridge regression. So this is an idea that dates back to Hurl and Kennard in a technometrics paper from 1970. Okay, so I'm going to consider my linear model again, but parameterize just slightly differently. I'm going to treat separately the intercept term from the other variables. So this 1n is just a vector of 1s of length n, and I've got some intercept parameter beta 0. Then I've got all my other variables in here. Where we assume that each column of x, which I'll write as xij, is centered so that the sum from I equals 1 up to n of xij is 0 for all j. Okay? So suppose the columns of x are nearly linearly dependent. Which is typically the case when P is nearly as large as n. So if P is bigger than n, then the columns must be linearly dependent. But I'm not necessarily quite going that far yet. But let's say P is half as big as n and n's big, then actually the columns of x will typically be very close to linearly dependent. Then the determinant of x transpose x, which is the square of the volume of the parallelepiped spanned by the columns of x is small. Okay? So that's saying that this is the product of the eigenvalues of x transpose x is going to be very small. So at least one, and typically many eigenvalues of x transpose x inverse will be large. Since we recall that beta hat has got x transpose x inverse in its covariance matrix, this means that at least one component of beta hat has large variance. So in many ways, the moral of high dimensions is it's the variance that kills you. The estimator is still unbiased, but now the variance is really big. Okay? And what people realize gradually over time is that by shrinking your estimator towards the origin, you're of course introducing a bias when you do that, but your hope is that it'll be more than compensated by a reduction in variance. Okay? So if you think of the mean squared error as the sum of the squared bias and the variance, then your hope will be that what you gain by reducing the variance more than outweighs what you lose from introducing a bias. Okay? So perhaps I'll write something to those effects. If we shrink beta hat towards the origin, we introduce a bias, but we hope this will be more than compensated by a reduction in variance. And this is the idea behind the ridge regression estimator. So for lambda greater than 0, the ridge regression estimator is beta hat r lambda, so r for ridge, and lambda is going to be a tuning parameter, where beta hat 0 and beta hat r lambda minimizes what I'll call Q2 of beta 0 and beta. So this is like a residual sum of squares term plus lambda times the sum of the squares of the coefficients. Okay? So my least squares estimator, or maximum likelihood estimator in the case of Gaussian errors, minimizes just this term alone. But what I'm doing here is I'm adding a penalty that penalizes having large values of beta hat. Okay? So it's shrinking my estimator towards the origin compared with the maximum likelihood estimator. This is called an L2 penalty. It's really an L2 squared penalty. And what lambda is doing is controlling the trade-off between the extent to which I want to be respectful of the data, there's fidelity to the fit term here, and the extent to which I want to shrink towards the origin. Okay? So if I've got a really big value of lambda, that means that I'm shrinking, I'm putting a huge penalty on having large values of beta, and therefore I'm doing a lot of shrinkage towards the origin. Conversely, if I've got a small value of lambda, then I'm getting something very close to the least squares fit. Okay? Okay, I think I will pause there and we can have a 10-minute break or something, and I'll come back in. Let's start again at 22. This is the definition of the ridge regression estimator that minimizes this L2 penalized least squares loss function. And one thing that's interesting to note is that we do not penalize the intercept coefficient. So we're only starting this sum from j as 1, not from j as 0. And why do we do that? To preserve location equivariance. So this refers to the fact that it shouldn't matter whether I add a constant to all my observations and then compute fitted values, or compute fitted values and then add a constant to them. Okay, those two operations should commute. And if you have a location equivariant estimator, they do. And in the way we've constructed it is location equivariant. However, the estimator is not scale equivariant. So if I make a scale transformation to my data and then estimate, that's not the same thing as what I get by estimating and then making a scale transformation. And the way we deal with this, or the standard way of dealing with this, is to normalize each column of x to have Euclidean length equal to the square root of a. So that's the same Euclidean length as a vector of 1s would have. Okay? And then a straightforward exercise is to actually write down the closed form expression for the ridge regression estimator. So we can write it as x transpose x plus lambda I inverse x transpose y. So this is a rather similar form to the original maximum likelihood estimator. It's just that we've added in this lambda I before we compute the inverse. Okay? This has the effect of moving all of the eigenvalues away from 0, right? Before you take the inverse. So it's sort of stabilizing this matrix in some way. Now, okay, we've come up with an algorithm. We've shown it's got a closed form, but in what sense might this be a good estimator of beta. So we've already seen the properties that my original maximum likelihood estimator has. So this is going to be theorem 2. I'm going to assume for simplicity that x transpose x is positive definite. My claim is that for sufficiently small positive lambda, we have that the mean squared error matrix formed by the ridge regression estimator is strictly smaller than the mean squared error matrix that you get using the maximum likelihood estimator. Okay, so I'm comparing a matrix with a matrix, and this ordering is in the usual matrix ordering sense. So I'm saying that this matrix minus this matrix is a positive definite matrix. Okay. So this is somehow surprising, but it does confirm for us that this trade-off of reduction in variance against increase in bias can be in our favour, at least for sufficiently small lambda. Okay. So the proof is a rather direct calculation. First, let's think about the bias of the ridge regression estimator. So that's its expected value. It's just a linear transformation of my y. And then I've got to subtract off this beta. Sorry, there shouldn't be a bracket there. And this I can write as, if I just think about adding lambda I and subtracting lambda I here, then I can write this as minus lambda times x transpose x plus lambda I inverse times beta. Okay. Moreover, so that's a bias. Now I can think about the covariance matrix of this estimator. But again, it's just a linear transformation of my y. The y is the only random thing here. So computing the covariance matrix just amounts to putting the matrix here, computing the covariance of y, and then putting the transpose of the matrix. So this is x transpose x plus lambda I inverse x transpose times the covariance of y times x transpose x plus lambda I inverse. Okay. But the covariance matrix of y is just sigma squared times the identity. So I get an expression like this. Well, let me do this the other way around. I'm going to look at the right-hand side minus the left-hand side. So I'm putting this all together. This is the matrix I want to show as positive definite. So the mean squared error matrix of the usual maximum likelihood estimator is just sigma squared times x transpose x inverse. Then I've got to subtract off the square of the bias and subtract off the covariance of the ridge regression estimator. So that's sigma squared x transpose x plus lambda I inverse x transpose x plus lambda I inverse. And then I'm going to subtract off the square of this guy, which is lambda squared times x transpose x plus lambda I inverse beta beta transpose x transpose x plus lambda I inverse. Okay? And this is what I've got to show is positive for sufficiently small lambda. And what you'll notice is that you've got three terms here, and these two both have a pre-factor and a post-factor which are identical, and I can factorize them out at either end. And then we'll have to adjust this term here. So let's see how we can do that. So I keep, no, I'm not going to keep that out. So I've got x transpose x plus lambda I inverse, and now the main term I care about is, well, let's put back what I took out. Then I've got an x transpose x inverse and x transpose x plus lambda I. Then this term simplifies a lot and just gives me a sigma squared times x transpose x. And then this one, I've got a minus lambda squared times beta beta transpose. And what's left is x transpose x plus lambda I inverse. Okay? So these terms are positive definite. So all I've got to show is that this matrix in the middle is positive definite. But if I look at this, this is just a quadratic in lambda. And it's actually a quadratic with zero zeroth order coefficient. Because this x transpose x, x transpose x inverse, x transpose x cancels with this term, at least provided I remember to put a sigma squared there, which should have been there. So overall, I'm getting x transpose x plus lambda I inverse, and then I've got 2 lambda sigma squared times x transpose x. Oh, no, x transpose x there, sorry. Times the identity matrix. And then plus lambda squared times sigma squared x transpose x inverse, and then minus lambda squared beta beta transpose. So my point is that I've got a lambda term and 2 lambda squared terms here. But for sufficiently small lambda, it's going to be this term that's going to dominate, right? And this term is a positive definite matrix. So this indeed will be positive for sufficiently small positive lambda. So that's, I think, a very interesting result, but it's important to understand its limitations as well as its attractions. So the lambda that I need in order for this to be smaller than this depends on things I don't know. It depends on the sigma squared, but it also depends on the beta. Okay? So I'm not actually giving you an algorithm which shows that the ridge regression estimator has a risk function that strictly dominates that of the maximum likelihood estimator. The lambda that I need here depends upon the unknown parameters. Okay? So that's the sort of limitation of that result, even though I still think it's an interesting result. Okay, any questions about the ridge regression estimator? Okay, let me say something about model selection now. So we've seen that the ridge regression estimator may help to reduce the mean squared error, but it doesn't help choose a model. All of the coefficients will still be non-zero in the estimate. Okay? And so although we may initially want to consider many possible covariates, so as to avoid modeling biases, there are several reasons for preferring a smaller final model. So the first is that we may reduce the mean squared error. So if we set things to 0, we know we're going to get 0 variance there. Of course, that may not be the right thing to do. Certainly, an undoubted advantage is that we have greater interpretability. So if you've got fewer covariates in your model, you can hope to understand the data generating process much more easily. And the third, which is probably a bit controversial, is a belief, or at least a hope, in sparsity. Okay? So a lot of the work in high-dimensional statistics was motivated by microarray experiments in genetics, and there you certainly might hope, although it's not clear that this is in fact the case in practice, but you might hope that it's a relatively small number of genes that are having the effect that are responsible for the effect that you're observing. In many, many other contexts, statisticians now exploit sparsity, but it's not so clear that this is really something that is satisfied by the kind of true unknown data generating mechanism, or whether it's just a convenient assumption for statisticians to use in their model. I think in many cases, if we're honest, it's the latter. But nevertheless, it is a very convenient assumption, and it's one that we're going to be working with. Okay, so here are a few classical model selection strategies. The first is called best subset regression. So here we start with the intercept just beta hat 0, which is the mean of the y's, and let's see. For k equals 1 up to p, maybe I'll put square brackets around here. Choose beta hat k to minimize the residual sum of squares, beta, which is defined to be the least squares objective function, with my intercept term plugged in over all beta into r to the p with at most k non-zero entries. Okay? So I can do this for each different value of k, and for a fixed value of k, in some sense, this is giving me, so if we think of a number of predictors, models with the same number of predictors as being on the same scale, then this is giving me the one with the best fit to the data. Okay? But then I've got to choose k, and it can be made by minimizing either the AIC. Who's heard of AIC? Okay, so this is minus twice the fitted log likelihood evaluated at my estimator here plus 2k. So this was proposed by Akaike in 1974. He had the cunning idea of calling it an information criterion, but it's now been renamed as Akaike's information criterion. And then there's BIC, which is almost the same guy, but you add a stronger penalty. So this is a Bayesian information criterion due to Schwartz in 1978. And instead of having twice the number of parameters in your model that you're penalizing it by k times log n now. Okay? So pretty much nowadays you could put any letter in front of IC and you'll find that there's a paper with someone proposing a model selection strategy based on some different penalty. That's a little bit facetious, but only a little bit. Okay, so what are the difficulties here? Well, this strategy involves exploring all 2 to the p submodels. So it's only really viable when p is less than or equal to 100. In fact, at least until recently, I would have said rather less than that, maybe 30 or 40. But there have been some quite interesting advances in integer programming that means that we can go much further than we could before. But 100 is still pretty limited for a lot of practical applications. And even if we could double that to 200, I mean, this guy is growing very fast with p, right? So that's a strategy with its limitations. Here's another strategy called forward selection. This is a greedy algorithm. It says start with the intercept and at each stage add the variable giving the largest reduction in the residual sum of squares, and then refit the model with the new variable included. Okay? That's a kind of sensible, naive strategy. This yields we're going to get a sequence as we add more and more variables. We have to decide when to stop. And we do this purely on a marginal basis. Well, the traditional strategy for doing this is to do it on a marginal basis. So you just look at whether the reduction in residual sum of squares in going from step k to step k plus 1 is sufficient to justify including the extra variable in your model, and we can do that using an F ratio as I described in the previous hour. So this yields a sequence beta hat F for forward selection 0, beta hat F 1, and so on, and we stop when, let's think about the residual sum of squares with this k here minus the residual sum of squares at the k plus 1 step. So I'm dividing this by 1, but then I've got to do 1 over n minus k minus 2 as the residual sum of squares in the larger model. So I stop if this is smaller than this upper alpha point of the F distribution with 1 and n minus k minus 2 degrees of freedom. So this is just the same thing as the F ratio that I wrote down at the beginning. We're just adding one more variable. So there are several things that make this not quite as satisfactory as one would like. One is, of course, it's a greedy procedure. So as with all greedy procedures, if you go wrong at the beginning, then you've got the potential to go really, really wrong. Okay? Another issue is that there's a multiple testing question about the fact that you're doing many tests of this form and you're not accounting for multiplicity in your inferential statement. And there's another drawback which I will mention in a moment after I've talked about backward selection as my third traditional model selection strategy. And this, you can probably guess, involves starting with the full model and at each stage remove the variable giving the smallest increase in the residual sum of squares, and then refit the model. Use an F ratio as above to determine where to stop. So, again, another greedy procedure, another one that's got a multiple testing issue. But there's another problem, which is the following. You might think about the following strategy. Use forward selection until your F ratio tells you shouldn't add any more variables. Then start from there and use backward selection until your F ratio tells you you shouldn't remove any more variables. And then use forward selection again until you don't need to include any more variables, and keep alternating. The trouble is that with that procedure, there's no guarantee that you're going to converge to any kind of optimum. Okay? So I don't find any of these three model selection strategies very satisfactory, but that was the situation we were in the mid-90s. Okay? So not much happened in the 80s. We've seen a couple of things from the 70s. Not much happened in the 80s. And now we're going to move on to what I think has been one of the most important developments in statistics, in modern statistics. In fact, you could in some ways regard it as the birth of high-dimensional statistics. And this is the idea of the lasso. So this is due to Rob Tibshirani from 1996. Okay, so the least absolute shrinkage and selection operator which rather conveniently abbreviates to the lasso. You might think he came up with the acronym first. Who am I to say? Okay, let me just say that this 2.1, this is going to be a definition and an introduction. So again, it's got a tuning parameter lambda, and I'll write L for lasso. So it's going to be somewhat similarly defined to the ridge regression estimator. We're now defining a new objective function, which I'll write as Q1. I normalize my least squares objective function just for convenience, because that's the usual way it's done. But instead of penalizing the L2 squared norm of the vector of regression coefficients, I'm now using the L1 norm to penalize. Okay? It looks like only a small difference, but it actually has a colossal effect in a certain sense. So okay. Remarkably, it turns out that beta hat L lambda typically sets some, or often many, coefficients to be exactly 0. So this is possibly the most important thing I'll say today. It therefore facilitates simultaneous model selection and parameter estimation. This is a really beautiful thing. I talked about these traditional model selection strategies. I didn't talk about yet another disadvantage of them. So what often happens amongst applied statisticians is they have a data set, they play around with several different models for their data, including terms, deleting terms, transforming variables, doing all sorts of things. And then once they find a model that they like and they settle on, they report the uncertainty as if they'd never looked at another model in their lives, right? Now, we all know this is not a valid way of doing statistical inference, and yet it happens absolutely routinely in applied statistics. And the disastrous fact about it is that you're erring on the wrong side, if anything. Your confidence intervals are going to be too narrow because you're overconfident of your conclusions. You're under reporting the uncertainty because you're not accounting for the model uncertainty. So this has a very attractive feature that it's doing a simultaneous model selection and parameter estimation. Now, it remains a very difficult challenge and one that's only been very recently addressed as to how you can report uncertainty based on lasso type of estimates. But nevertheless, you've got a much better chance than you have of really adequately summarizing your uncertainty by the time you've transformed some variables, played around, fitted different models, plotted some graphs, used the graphs to inform what model you should fit. Then you're really in a disastrous position when it comes to formally quantifying your uncertainty. So this is much more of a modern paradigm and much, much more effective when it comes to high-dimensional data. I mean, if you've only got 3 possible variables to include in your model, it maybe doesn't matter so much if you play around with a few different models. But if you've got p in the thousands and you're playing around with tens of thousands of models, then really you're not doing justice if you report the uncertainty, you report your confidence intervals as if you'd never looked at another model. Okay?
Does that feel better with correlated predictors?
What would you mean by better?
Will it be easier for it to select a model if you have a lot of correlated predictors?
I mean, if you've got highly correlated predictors, it's always, I mean, that's just a fundamentally challenging problem to, you know, you've got predictors that are virtually aligned. How do I know whether this one should be my model or this one, right?
Or a linear combination.
Right. I mean, that's just a challenging problem.
Yeah.
And I'll say something a little bit more about that in the next hour. There's something called the elastic net that was introduced that actually involves a convex combination of an L1 penalty and an L2 squared penalty. And that's specifically designed for situations where you have highly correlated variables. Okay, so it's convenient to replace yi with yi minus y bar. So I'm just centering my responses. So then I can see that this guy actually minimizes a slightly simpler function, and with a slight abuse of notation, I'll call this Q1 of beta. Over beta in R to the p. So here is my L1 norm. It's just the same thing as I've got written down here. It also minimizes I can think of this in 2 different ways. This is very much, should remind you of constrained optimization problems where this is a Lagrangian term, right? So I can think of this as minimizing my least squares objective function subject to an L1 norm being less than or equal to S, or equivalently as minimizing an L1 norm subject to my least squares objective function being less than or equal to t for some S, which is a function of lambda, and t, which is a function of lambda. Okay? So let's see if we can get some intuition about what's going on here with the lasso. For intuition, consider the orthogonal design setting where 1 over n x transpose x is the identity matrix. Okay? In particular, this means that p is less than or equal to n. So this is definitely a very restricted situation, but it's one where we're going to be able to explicitly write down what the lasso solution is, and that'll give us some intuition about what's going on. In this case, my original maximum likelihood estimator simplifies because 1 over n x transpose x is the identity, and writing y hat equals x beta hat, I can simplify this q1 of beta by subtracting and adding y hat in here, and what I see is that I get a y minus y hat squared plus, and the cross term cancels, and the other term is a simple one, like this. And this is what I want to minimize over beta. But what can you tell me? What's nice about this expression here? People online are shouting at the screen. Sorry? It's convex, that's certainly true, but this is always convex in beta, regardless of whether I got orthogonal design. So what's special about the orthogonal design setting here? Not everything is known. No, I still don't know what the solution is yet. Okay, the point is that this term doesn't depend on beta, so in minimizing it I can ignore it. But look at these two terms. This is a sum from j equals 1 to p of these guys, but the L1 norm is also a sum over the different components, right? What this is telling me is it suffices to minimize over each component separately. In other words, I can just do p univariate problems. Much, much easier than a p-variate problem. Yeah.
Why don't you choose the convexity? Why don't you choose the convexity?
Why don't I use the convexity? Here, you mean? Yeah. So the convexity will guarantee that the solution exists. It won't. Why
ensure that it's always convex?
Why ensure?
What ensures?
What ensures that it's convex? Oh, okay. So this is a linear transformation of beta. Okay, so this is a convex. This is the L2 squared norm. That's a convex function. And then I'm adding it to another convex function, this L1 norm of beta. This is a convex function. So it's a sum of two convex functions. Yeah, so the point is that I can minimize over each component separately. And we can get an analytic solution which says that the jth component of my lasso estimator is equal to the sine of my maximum likelihood estimator in its jth coordinate times, and then I've got to take the absolute value of the jth coordinate, subtract lambda, and then take its positive part. Okay? So, in other words, this sine SGN function is 1 if its argument is positive, it's 0 if its argument is 0, and it's minus 1 if its argument is negative. So, thus, in this case, the lasso is a component-wise soft thresholding estimator. Okay, so this is the line y equals x. So this is, if I do no shrinking, I just stay on the line y equals x. But what my lasso is doing is this. In other words, everything whose absolute value is less than or equal to lambda is getting shrunk to be exactly 0. Okay, that's what's helping me do the model selection. But if the absolute values of the original maximum likelihood estimator component is sufficiently large, then it doesn't get set to 0. It just gets soft thresholded, so brought down by lambda in absolute value. For further intuition, consider the case p equals 2. Okay, so this is a sort of simplest non-trivial example. So I've got a beta 1 and a beta 2, and I'm going to compare the ridge regression solution with the lasso solution. So with the ridge regression estimator, the contours of my constraint set are circles, and if this is my maximum likelihood estimator beta hat, then the contours of the least squares objective function are ellipses. And my ridge regression estimator is found at the intersection of these contours. Okay? That's a standard fact about convex optimization. Now let's think about the lasso solution. Now the contours of the L1 ball are like diamonds. And if here's my maximum likelihood estimator again with its elliptical contours, what you see is there's a decent chance that the intersection occurs at a corner of the L1 ball. But a corner of the L1 ball corresponds to a place where one of the coordinates is 0. So again, it's setting some of the components to be 0. Any questions? Okay, let me very quickly do an example to see this in practice, and then we can have another break.
What if it's L0 norm? How do you
The L0 norm is not a convex, so the contours aren't convex, so you can't quite use this analogy. But in many ways, you're using the L1 norm to approximate the L0 solution. So the usual way that lasso solutions are computed in R is using a package called glmnet. So what I'm going to do is I'm going to have 100 observations in 1,000 dimensions. Okay? So it's a pretty challenging problem. And I'm going to construct my coefficient beta so that the first 10 of these variables are non-zero, and then the remaining p minus 10, that's 990, are 0. Okay? So if I look at the first 20 components of beta, I've got things like this, okay, and then zeros from there onwards. So now I'm going to construct my design matrix, which is going to be a matrix of normal random variables, standard normal random variables, an n by p design matrix. And now my response is going to be x times beta plus some error, like that. Okay? Then the output I want is to apply the glnnet function with inputs x and y, and I've got to tell it that I'm working with a Gaussian family. And bear in mind, we've got 100 observations, 1,000 variables, and we're going to compute an entire path of solutions as lambda varies. Okay? That's a pretty challenging convex optimization problem. Let's see how long it takes. And this is a pretty crappy laptop. Not long, right? So let's see what this looks like. This isn't as readable as I'd hoped. Never mind. Okay, so well, I can see, I'm sure you can't, that these numbers here are the numbers of the individual coefficients. Okay, and perhaps it's just about clear that these are single-digit numbers. So these are all my signal variables which are coming out. And these ones here are all the sort of the other ones which are in a complete mess here. So in particular, let's look at, this is coefficient 1, I think. If I go back and look at what it was when I generated it, it was both large and positive. It's 3.17. Okay? So that's not so surprising that this is coming out large and positive. Let's find another one, 8.32. That should be number 5. I really can't read it well enough, actually. I'm not quite confident what the numbers are. Anyway, if my screen resolution were better suited, you could actually see what the numbers are. Now, this was a relatively easy problem in the sense that the signals were strong. Okay, I gave them standard deviation 5. Let's say I make the problem more challenging and I go 0.5. So now if I look at my signal strengths, you see they're much smaller. Okay? And again, I'm going to compute my y like this, play the same game at computing the solution, and now plot it. And now I see a very different sort of picture, right? I've got noise variables and signal variables which are entering the model. These I can see as single-digit numbers, so that the sort of the big ones are still coming out, but there's probably no point on this curve where I can fix a lambda. So this would amount to fixing a lambda and say, okay, these are the right variables. Whereas in the previous setting, the signal strength was large enough that I could choose a range of lambda values where I was getting all the signal variables and none of the noise variables. Okay? So that's just easy problem versus hard problem. Okay? So after a break, what we're going to do is have a look at some of the theoretical properties of the lasso, and if I have time, I'll say something about how you compute it as quickly as this. Okay, let's come back. Okay, so now I'm going to talk about the theoretical properties of the lasso. So let's assume that y is beta 0 times a vector of 1s plus x beta plus epsilon, where each column of x is centered and scaled to have Euclidean length root n, and where epsilon is standard normal. I need some notation for a matrix A in R to the n by p, B in R to the p, and a subset S of 1 up to p. Let AS denote the n by cardinality of S matrix obtained by extracting the columns with indices in S, and let BS in R to the cardinality of S be the vector obtained by extracting the entries of B with indices in S. Okay? Now I'm going to fix my particular S that I'm interested in. That's the set of components where beta j is non-zero. So it's my signal set. I define my noise set to be the set where beta j is 0, and let S, so little s, be the cardinality of big S. Okay? So I need one condition on my design matrix for the estimation and prediction properties. So to study the estimation and prediction properties of the lasso, we'll work with the following, what's called compatibility condition. So it's a little bit hard to get your head round, but let me write it down and then I'll try and say something about it. It says there exists a positive phi 0 such that for all B in R to the P, where the L1 norm of B on the noise set is less than or equal to 3 times the L1 norm on the signal set, we have that the L1 squared norm of B on the signal set is less than or equal to S times the squared Euclidean length of xb over n times phi 0 squared. Okay, so that looks a little bit unpleasant. It may not even be completely obvious that this is a condition on the design matrix, but it is a condition on the design matrix. So, remark, if we replace this guy BS1 squared with its upper bound, that is, we weaken the condition, strengthen the condition, this would be called a restricted eigenvalue condition. So you see that term used quite a lot in the literature, because without the Bn less than or equal to 3 times the L1 norm on the signal set condition, or restriction perhaps I should say to emphasize it, we would require that X transpose X be positive definite. So this is saying something about the conditions, the directions in which X transpose X needs to not map things to 0. Okay, so when P is bigger than n, I know that this can't be a positive definite matrix anymore, but I'm asking for nice behavior in certain directions. Okay, now these are not directions that I know in advance because I don't know what the noise set and the signal set are. Nevertheless, this is an assumption I require on the underlying data generating mechanism in order for me to be able to prove something about the estimation and prediction properties of the lasso. So this is a variant of a result in a paper, well-known paper by Bickel, Ritov, and Sivakov from 7 years ago now. Okay, this is pretty much the kind of final word on the finite sample estimation and theoretical and prediction properties of the lasso. So let's assume my compatibility condition, and I'm going to define my lambda to be A times sigma times the square root of log P over n. My claim is that with probability at least 1 minus P to the minus A squared over 8 minus 1, I can say that the average prediction error plus lambda over 2 times the estimation error in L1 norm now is bounded by 3a squared over phi 0 squared, which is like a constant, times sigma squared s log P over n. Okay? So that might look a little bit complicated, but let me try and explain what it's saying. So this is simultaneously giving me control of the average prediction error on the observations and the estimation error. Okay? So I can cover this term up, and I'm still bounding the prediction error by this guy. And you should compare this result with what we saw in the first hour, where we looked at this expected difference in the linear model, right? And there we saw we got sigma squared times P over n. Well, now the true dimensionality of my model is S. This is the number of non-zero variables, right? So I'm getting the same sort of sigma squared S over n to what I had before, but I've also got a log P factor here. So the moral of this theorem is that you pay a price of log P for not knowing which of the variables are true signal variables and which of them are noise variables. Now, because log only grows very slowly with dimensionality, we typically think this is a relatively small price to pay, and you might as well try and include a lot of variables that you think may be relevant in advance, okay? So it's a similar story for the estimation properties. Because I've defined my lambda like this, I can cancel off a square root of log p and cancel off a root n, and I get a very similar story to what I had in the low-dimensional linear model case, where I'm paying a logarithmic penalty for my absence of knowledge of which are the true variables that I need in my model. Okay, so that's one of the most important moral messages to take away from about the lasso. So there's a lot that I really like about this result, exactly as I just explained. What are the limitations of the result? Well, one is, as I've already explained, you can't check this condition in practice. You don't know whether this holds or not from your data. So you have to be willing to assume that in order to have this probability bound. Another thing is, it's not a completely data-driven procedure in the sense that the lambda that I'm choosing depends on something I don't know. It depends on the sigma, the noise variance, or noise standard deviation. That's not too serious. That's something you can estimate, and actually you can do it simultaneously with the square root lasso and do things a little differently. That's not really too much of a problem, but anyway, that's there. And then the other fact is that this prefactor here, this constant factor, could be pretty large, right? I've got a 3, but in order to be able to conclude this with high probability, I'm certainly going to need a squared to be bigger than 8, right? So this number is going to be at least 24, and then this phi 0 squared I can show is certainly going to be smaller than 1. So this constant here could be really quite large, and actually probably will dwarf the log p factor. Nevertheless, we tend to not worry too much about this constant factor, and we think of just paying a log p penalty for the absence of knowledge of the signal set.
Is it a matrix or is
It is?
it a matrix? Or
No, it's a scalar. Yeah. Yeah. Any other questions? Okay, so that's one of my big theorems. It's not that difficult to prove, actually. If I were teaching this at sort of master's level or something, I would prove it. But probably not quite right for this audience. Okay, one big theorem deserves another. So now I want to talk about the variable selection properties of the lasso. When can I be confident that I'm recovering the true set of signal variables with my estimate, okay, and not getting too many noise variables? So we now consider the variable selection properties of the lasso. So this is another variant of a result by Martin Wainwright, again from 2009. Okay, so for simplicity, consider the noiseless case where epsilon is 0. So I've got no noise at all. This is not essential, but it'll simplify things a little bit. And assume that XS transpose XS is positive definite. So this is a very weak assumption. I certainly wouldn't want to assume X transpose X is positive definite, because that would rule out P being bigger than N. But I'm typically thinking of the signal set being relatively small, and so having linearly independent columns amongst those guys is a pretty weak condition. So I'm going to define a vector theta, which is xn transpose xs times xs transpose xs inverse times a vector of signs of beta s. Okay, I'll say something about that definition in a moment. So the claim is that if every entry of theta is bounded in absolute value by 1 and the absolute value of beta j is bigger than lambda times the sign of beta s transpose times the inverse of this and take its jth column for j in S, then there exists a lasso solution beta hat L lambda whose vector of signs agrees with the vector of signs of the true beta. Okay? So there are two conditions, but if those conditions are satisfied, then I can find a lasso solution that on the signal set is giving me something non-zero, and on the noise set is giving me exactly 0. Okay? As a partial converse, if there exists a lasso solution beta hat L lambda whose signs agree with those of the true vector, then the L infinity norm of theta is less than or equal to 1. Okay? So I'm not saying anything about the this condition here, but certainly this other one is satisfied. Okay, so now let's try and understand what these two conditions are saying. This one is probably the easier of the two to understand. It's saying that on my signal set, my non-zero guys need to be sufficiently large. Well, you should definitely expect a condition of that type. It's often called a beta-min condition in the literature. If I've got a variable that's non-zero but absolutely tiny, how can I realistically expect my lasso solution to know whether that's 0 or non-zero? Okay, I can't. So I need a sort of sufficiently strong signal to be able to get the right sign vector. And then there's this condition here. And well, I'll say something, I'll write something about this in a moment, but this is somehow talking about, it's saying no noise variable can be highly correlated with signal variables. Okay? Because if I've got noise variables and signal variables which are highly correlated, it's going to be extremely difficult for me to know which of them is really needed for my model, which of them is a signal variable, and which one is a noise variable. So those are the two conditions, and they're very intuitive conditions, I think, that I need to be satisfied in order for my lasso to select the right variables. And you should think of these conditions as being strong. Okay? You're asking for a very strong conclusion. You're getting every single sign coefficient right. All the non-zeros are declared to be non-zero. All the zeros are declared to be 0. That's a very strong conclusion. You should expect to require very strong hypotheses for that to be true. Okay? So let me just give a remark about this then. So for j and n, so for my noise variables, theta j is the inner product of this vector of signs with the vector of regression coefficients obtained by regressing xj on my signal variables. Okay? So the condition that the L infinity norm of theta is less than or equal to 1 is known as an irrepresentable condition. So you see that term used in the literature a lot. So it's saying that no noise variable is too highly correlated with signal variables. Again, a very intuitive condition that we should expect to require in order to get the vector of signs correct. Okay, any questions about that? So that was really all I was planning to say about the theoretical properties of the lasso. Yeah?
Are there any multi-scale equivalents of lasso? Where you have these nice properties in clumps and then you have another clump and you can somehow recursively run a lasso? You see what I'm saying? So you have 10,000 dimensions. Actually, it's not going to work over 10,000 dimensions. It's going to work over 10 clumps of 1,000 dimensions.
Yes, yes. So there's a very well-known paper called the group lasso, where you exactly expect sparsity at the group level. It's written by Ming Yuan and Yi Lin in 2006. It's had well over 3,000 citations, so that was a good idea. Yeah. So what you end up doing is penalizing the L2 norm of the coefficients within a group, and that encourages group sparsity. So all the variables in a group are either selected or not selected. Okay. So the last thing I want to talk about today is computation. So we saw that algorithms can compute the lasso extremely quickly nowadays. Okay, so how are we doing this? These days, lasso solutions are usually computed via coordinate descent. This is a general way of minimizing functions f from r to the p to r of the form f of x equals g of x plus a sum of hj of xj, where g from r to the p to r is convex and differentiable, and each hj as a function on r is convex. Okay? So this is exactly the situation we've got with the lasso. We've got a smooth convex function, the L2 squared norm, the least squares objective function, and then we've got a one that's not smooth, so I'm not insisting that each hj is smooth, but it is convex and it decomposes as a sum of additive terms. Okay? So here's the general strategy. We start with an initial guess x0, for instance, x0 equals 0, and for m equals 1, 2, and so on. So coordinate descent is a rather simple algorithm. So at the mth iteration, we set xm1 to be the argmin over x1 in R of f of x1, x2, m minus 1 up to xp, m minus 1. And then for the second coordinate, we define it to be the argmin over x2 in R of f. And now we plug in this with its mth value, not the m minus 1th guy, x2, and we keep the other ones as they were. And we keep going, we keep updating the coordinates one by one until at the last stage, in every coordinate up to the p minus 1th, we can take the mth iteration guy. Okay? So this is rather like Gibbs sampling. Who's seen this with Gibbs sampling? No? If anyone did MCMC, then this should be sort of familiar, right? Okay. So what can we say about its convergence? Well, Seng in 2001 proved that if a set which I'll call A0, which is a set of points where f of x is less than or equal to f of x0, is compact, then every convergent subsequence of the sequence xm converges to a minimizer of f. Okay? So in our case, this set definitely is compact because my objective function blows up to infinity in the tails. So the set where I'm smaller than wherever I start, is certainly a compact set. Since actually my sequence is always improving my objective function, if A0 is compact, then this sequence is wandering around in a compact space. So actually, every subsequence of xm has a further subsequence converging to a minimizer of f. Okay? But that's very interesting because it means in particular if f has a unique minimum, at x star, say, then xm converges to x star. So the algorithm converges as I like. So the only issue is, so let's say I've got two minimizers of this function f. What I can't rule out is the possibility that I could be sort of alternating, my algorithm could be alternating between being very close to one and being very close to the other. Right? But if I've got a unique minimum, then I've got this sequence that's wandering around in this compact set. That means every subsequence of it has got a further subsequence that converges. And if the minimum is unique, that further subsequence must be converging to that minimum. But it's a basic result from the sort of first course in analysis that xn converges to x if and only if every subsequence of xn has a further subsequence that converges to x. Right? So that's a kind of nice result, I think. Okay. Thus, in order to compute the lasso solutions on a grid, and where we start is at the smallest value of lambda that gives me a solution equal to 0, and it's not hard to show that that smallest value of lambda is exactly the L infinity norm of x transpose y divided by n, and then I keep going down, so I'm getting these non-trivial solutions down to lambda L. We start with beta hat L at lambda 0 being 0, because that is this, we know that is the solution, and use the previous solution as a warm start. Okay, so once I've got it at a solution at a particular value of lambda, that's where I'm going to start when it comes to looking for my solution at a smaller value of lambda. So this can be combined with an active set strategy as follows. So I'm going to initialize my active set at the nth iteration to be the set of coordinates for which my solution at the L-1th iteration were non-zero. Okay? In step 2, I perform coordinate descent only on the coordinates in AL. Okay? So I'm not cycling through all of these guys. I'm only going over a restricted subset of them. Yielding a candidate solution, which I'll call beta hat, where I'm padding out the values of beta hat off the active set with zeros. So having computed that candidate solution, I need to check if it is a solution. And I can do that. So if any of you are familiar with convex optimization, you'll know that the optimal solution is defined by the KKT conditions, right? The Kuhn-Kurush-Tucker solutions. So it turns out that the KKT conditions in this case, it's not difficult to show, that they amount to checking whether or not for every variable this guy is less than or equal to lambda. Okay? So V is my set of violators. So these are the violators of my KKT conditions. If V is empty, then I know I've got a solution, and I can output beta hat. Okay? Otherwise, I'm going to update my active set by adding in the violators and repeat step 2. Okay, so I go back and I perform coordinate descent again. And then I check if I've got violators. Now this is very quick because the individual coordinate descent steps only involve a soft thresholding operation. That's what we saw with once we fix every other coordinate. Okay? So that's why this algorithm is so fast and we're able to compute solutions in the blink of an eye. Okay, any questions? Well, if not, I think I'll stop there and thank you very much for your attention.